So we have this diester reacting with sodium ethoxide, followed by an acid workup. Then we follow that up with some form of acid, aqueous acid, and heat. What will be our final product? So we're first just going to draw out every step of the mechanism to show what our final product will be, because I think that's the most important. This will be some alpha chemistry. This is what this video is about, and showing a nice little alpha chemistry problem. So the first part is that we're going to make an enol. So let's take sodium ethoxide, our base, and let's make an enol. Right, that's what's most likely to happen. This hydrogen here, or that hydrogen up there, we'll just arbitrarily pick this one, is very reactive, right, because it's on an electron withdrawing ketone. So it's going to make an enol, so we're going to get this here. And I'm going to try my best to keep our, our bonds here as far away from each other as possible, so we don't get mixed up, although that is seeming to be quite challenging. So here we have our enol, our enolate, and you can see it has a negative charge. Now, what's likely to happen is we know that for a clasien, we know that a enol ester with another enol ester is going to probably attack that. So that's exactly what happens in the next step of the mechanism, where these electrons push our electrons to attack this carbon here. So we're going to get a ring. Now let's think about the size of the ring. We have this part here, attacks this carbon. And then we have the carbon here, so we're going to attach it as so. Let's see here. So we have, it went like that, like that. These problems always fuck with me. And then it's going to attach to this carbon, which then attached like this. So we have a bicyclic, and they're both pentane species. Okay, so that's the hard part out of the way. Now we have a negative charge, so most prominently we have an acid workup, and that's exactly what happens. Or actually, acid workup doesn't happen quite yet. We're going to push out this group here, because this is under basic conditions. We haven't added the acid yet. We know that before we add the acid, if it was acid in this, we would get ethanol, but we have our base, and it's still in basic solution, so this allows for the pushing off of an ethoxide group, because there's an equilibrium from the sodium ethoxide that we have. So sorry about the confusion there. We're going to push off that acid workup step will neutralize our base here to give us our product. Okay, so we have this ring here, and now we have H3O+. How does H3O+ react with heat? Well, we know that's beta decarboxylation, okay? Basically, we're gonna remove a CO2, but first we have to get rid of, if you remember from the carboxylic acid chemistry, if we have an ester, we use H3O+ and acid. That's gonna get rid of that there. So what happens first is we're gonna activate the carbonyl by adding a positive charge to it. So we steal a hydrogen, and we get this compound. Oh geez, I should have drawn this better. Whatever. I'll just explain it. Notice we have a positive charge on that on that group there, making that this carbon is very reactive. So what happens next is just a molecule of water is going to come in. Water likes to attack, so it's going to do just that. We're going to get now this compound. We're going to get a OH group here, OHH positive. Wow, I'm really smushing stuff in, I apologize. Let me actually redraw it over here. We have space to do so. Just so I can get a little more space, we'll do it like this. Okay, so we have this compound here. We know that there will be some deprotonation, and actually, to make it simpler, we'll steal the hydrogen from here. We could take anything, just a species of water, for example. So water is going to come in and steal a proton, and we'll neutralize our OH. So notice we have a hydrate here with a group here that's ready to leave. What we can do is we can use an acid. We're going to use H3O+. Our ether will pick up. Our ether is going to pick up a hydrogen, and what this allows us to do, and let me make sure that this is visible what I'm drawing. What this allows us to do is for one of these OH groups to move and kick off the methoxy group here, and that should actually be ethanol. So sorry about that, I just destroyed a carbon. So we're going to remove we're going to remove an ethoxy group, and we're actually still going to get a positively charged species, but in this case we can go like this, and this is quickly converted into a carbonyl by a molecule of water taking a hydrogen. Now, that would be an equilibrium, granted, but it still happens, and that's why we would expect ourselves to get the carboxylic acid. Now, when you heat a carboxylic acid, what happens? Well, we get beta decarboxylation. How does that occur? For those that don't know, we simply take our, I'm trying to think, oh goodness, it's slipping my head. It's acid and heat. We take, right, so we have a species here. It's going to take the hydrogen we have a negative charge on our, this is called the carboxylate ion, because it's just a deprotonated carboxylic acid. So what happens next is these negative electrons push in, and they're going to kick out this here, and then it's going to push up the electrons. It's kind of shoving the electrons onto that carbonyl, and what we see is we're going to get an enolate from this. And we're actually going to remove this as CO2 gas. So it bubbles out of solution. When you get to this step, it's irreversible. All this stuff is in equilibrium. So it could go like that way or back, or go all through the snaking pathway. But as soon as it reaches this, and granted it's in an open vesicle, what's going to happen is the CO2 is going to evacuate, and it's going to be irreversible. Once you get to this step, you're basically good to go. Now this gets protonated. That's why our acid is important. This gives us an enol. And what happens to enols in the presence of acid? Well, they tautomerize, and I just want to make sure that I'm not going to be cut off here. They're going to tautomerize, right? We take our acid. We are going to have the carbonyl pick that up. And then, yeah, these electrons, they push down. Oh my goodness, this is a long mechanism. This problem is quite lengthy. So we now get that protonated carbonyl, which isn't what we want. And what we notice is our H2O. And I did omit something that I do want to make a point about here, which has to do with stereochemistry. Now, just to make sure I got the mechanism right, I kind of forgot. You can see here, I had the one step with this, and then I just quit. Well, notice how this is on a wedge here, right? We're predicting products. This was just to predict what product we get. But right here, we have a wedge. Now, this means that this will remain a wedge. And when we attack this, the ring isn't going to just go like sideways, right? That's too much strain. So it's going to want to equalize into an up position. So our, in this step, we actually remove the stereochemistry because of this alkene. Actually, do we? No, we don't. We don't get rid of it. So this should be a wedge too. I'm learning it. I'm learning things too, guys. But yeah, that turns into a wedge, and our final product, we would expect to retain the wedge. And that's our final product right there, where we keep it on a wedge. I'm sorry that I messed up a million times on this problem, but we got it right. It's a wedged ring. That's that problem. Have a good day.